I talked about analysis, and to get a clear analysis of the risk, we need to see what's happening there. We have here the physics, we have thermodynamics, and we have dynamics. We see here well what happened here. There is an enormous reservoir of methane and crude oil, and that's sitting there for years. I mean, nobody can name a name, and that you can say, okay, it was there since the birth of him. No, we're talking about the dinosaur. We're talking about even a lot earlier. So what do we have here? We have here the seabed, and on the seabed we have the BOP, the blowout preventer. Here we have the riser, that's the pipe that we put there now to bring the oil to the ship. And then we have here the drill pipe. So this is the riser, the BOP, and the drill pipe. The drill pipe is 3.4 miles long or deep. This is the rock seabed, and there the drill pipe goes through, up to the reservoir, or better, down to the reservoir. We are talking here about a pressure of 7,500 psi, or between 550 and 700 bar, which is quite a lot of pressure. From here, when we count from the sea level to the seabed, we have another, you see, 2,200 psi, or 150 to 160 bar. So count those two together, and that's minimum what's here. So we're talking about a pressure level that's more than 10,000 psi. What is in there? What is crude? Well, crude is actually a mixture of methane and hydrocarbons. The specific gravity or the specific density of crude in the Gulf is between 0.85 and 0.89. That means it's lighter. The water there, you can see, has a density of 1.020 to 1.030. So it's heavier than sweet water. If we talk about temperatures, here at the bottom of the well, we're talking about 300 degrees Fahrenheit, which is about 150 degrees Celsius. Here at the riser, when the riser starts at the bottom of the BOP, we have 40 degrees Fahrenheit, which is about a freezing 4.5 degrees Celsius. On top, we have about 70 degrees Fahrenheit, plus 18 degrees Celsius. Now, back to this page, you see in the crude, we have the mainstream. The mainstream is an amalgam mixture of the lighter components, the medium components. The heavy components are most bituminous. Bituminous, that means here I made a little part, a ball, and the bituminous ball has about the same specificity as water. It's situated here, so what's happening in the beginning, it will go up. When it's a little bit in the water and it loses the lighter components, it will sink down. If you float a while in the water, it will go down to the bottom, and this bituminous ball can be everywhere in the world. It's as simple as that. What does methane stand for? Methane is a gas, is there in liquid form, and we have two special things that we have to deal with methane. The hydrate flat rates, where PP was talking about when they used the dome, the big diamond, you remember? What's happened? When osmosis conditions are there, and you have liquid methane, and you're getting cold water, it starts becoming like an ice crystal. An ice crystal that's cold, or a hydrate, a flat rate, to be really complete, you need to call it a hydrate flat rate. Why? Normally, the flat rates, they are a vast mass. They are like a lump of ice, a block of ice. The hydrate flat rates can be ice on the outside, but can have still some liquid parts at the inside. Now, what's happening? The project with the containment dome didn't work because we had formation of a lot of those clatrates and they all wanted to climb up and they got restricted by the opening in the roof of the dome. So they couldn't pass and they froze the hole closed. They closed up, they closed up the hole. So what happened then? Well, because of the pressure, because of the difference in specific gravity, that dome was lifted and lifted and lifted again. So the solution is definitely not a small pipe. We come on that further. High-grade clatrates, they climb, they go in the ocean, and what's happening? They dissolve. They dissolve in a way that the ice will melt and the clatrates will become ice, water, and methane. The methane stays a little bit more liquid, and then it goes to the gas phase, because methane is a gas. So we call that sublimation. Sublimation has a specific problem with methane, because we go to the RPT. RPT stands for rapid phase transition. Now the rapid phase transition is known close to atmospheric pressure to give an expansion in volume of 600-700 times to the atmosphere. So that means an explosion without fire. So we need to deal with the RPT, we need to deal with the high-grade clatrates, and how to do it? Well, a completely different way. I'll show you further. This is actually a simple sketch of what we have. We have here the seabed, we have the BOP, and then we have here the water of the Gulf of Mexico. That BOP, the pipe in there, is spooling out the mixture that we discussed, so the oil, the methane, and it goes up to the ocean. What we see now is clatrates. I don't see no clatrates, no icebergs, nothing. So everything dissolves, everything looks fine, no problem. All the oil goes to the surface. Make it a thick layer of oil between the containment domes, and when the sea is a little bit rough, part of it goes underneath. Same there. The idea of the sleeve is very simple. It's just limit the space of expansion, because here this is pushed by the wind. Here are currents in several directions. So where is it going to end? Well, nobody knows on beforehand. The idea is just to get everything together to make a sleeve and to put it over the system. And here we do something else. I'll tell you later.